So in section 2.8, we're going to work with something called complex fractions. Complex does not just mean it's complicated. It's not like the English word complex and just it means complex. There's actually a definitional kind of term too. And complex fractions means you have fractions inside of fractions. That's what it really means to have a complex fraction. You have double fractions included. So the thing that I want you to remember with complex fractions that's really important is that division is the same as multiplying by the reciprocal. So if we attempt to divide by 6, it's equivalent, right? This double arrows means it's the same as multiplying by 1 over 6. If we're trying to divide by 4/3, it's equivalent to multiplying by the reciprocal 3/4. So we're going to use that fact extensively in what we're doing, okay? So the first ones we're going to do are going to start without any variables, and then we'll involve the variables with them. There aren't any differences to it. It just gets a little bit, builds on itself as we go. So in the first one, you can see, first 1 and 2 on this slide, you can see the fractions inside of fractions, right? And they look really awful. I mean, let's just be real. They don't look good. But what this means is that this is division, right? There's a division bar there. And you'll always be able to tell because the division bar between the pieces will have a thicker division bar where they're divided, okay? So like on the first one especially, you might be like, okay, well, is that the division bar or is it this one? Well, which one's bigger and thicker? This one. So that's the division bar we're talking about. So my numerator is this part 5/3, and my denominator is the 3. So another way of writing this, you don't necessarily have to write it out, but you're definitely going to be thinking of it this way, is that I have 5/3 divided by 3. If it helps you to see it written like that, write it. If not, don't worry about it. Either way, we're going to go either from where we are or from this version, and what we're going to do is we're going to take my 5/3, and instead of dividing by 3, we're going to multiply by the reciprocal, which is 3 over 1. I didn't write that right. 1 over 3. Sorry, I got distracted. 1 over 3. There we go. We're going to multiply by the reciprocal 1 over 3. Okay? That looks just like the things we've been doing. You can actually extend the division bar if you wish across here. We're multiplying across the top, multiply across the bottom. This is 5 over 9. So when you're done with a complex fraction, it should be a fraction that's in reduced form. It should be a fraction that has a single constant in the numerator, single constant in the denominator, or something like that. It doesn't have a fraction inside of a fraction when we're done. That's what we're looking for, and 5 over 9 doesn't simplify. Yep, Cameron?
Whenever you multiply the denominator, it stays the same? It's like on some problems, like when you're multiplying the denominator, it will stay the same.
I'm not sure what you're referring to. Multiplying the denominator, it stays the same.
Maybe it's not multiplying.
Keep thinking on it, and if you can. Oh, I think what you're thinking is what we did in the last section, where we added and subtracted fractions. The denominator stayed the same, and we actually just combined the numerators. That's addition and subtraction. Okay. We talked about that in terms of like a diagram where you think about like eating a pizza. If I eat 1/3 of the pizza and you eat 1/3 of the pizza, that's a total of 2/3 of the pizza, not 2/9. So that happens with addition. With multiplication, that does not happen. Yeah, you just multiply across the top, multiply across the bottom. On number 2, again, if it helps you to see it, rewrite it, go for it. You have 3/5 divided by 9/14. You don't have to write that, but if you can, if you wish. But what you do need to write is that this is 3/5 times, and we do the reciprocal 14 over 9. So you're always taking the second fraction, or the fraction that's in the denominator, and you're flipping it. You can look across diagonals to simplify. We've done fraction multiplication before. This is not our first time around with this. But you can do that here. You could do it at the end. I usually do it here because I like to keep my numbers a little bit smaller as I work. So I happen to notice that the 3 and the 9 are both divisible by 3. So 3 divided by 3 is 1, and 9 divided by 3 is 3. 14 and 5 don't have any ability to simplify. So then I multiply across the top, and then I multiply across the bottom. So I have 14 out of 15. Okay, so far so good? Okay. The next thing we're going to do is we're going to get some variables involved. Oh, I totally lied. I was thinking we were there yet. We're not. That's number 5. The next thing we're going to do is we're going to get some addition and subtraction involved. That's actually what's going to happen. So as we're taking a look at this, I do not have the ability to just multiply by the reciprocal of the denominator because the denominator is not a single fraction, right? It's just not. So there's a couple of different things I can do, and I'm going to show you both options, and then I'm going to use one of them from here on out because I think it's the easier option. If you like one of the options I show you and it's not the one I'm consistently using, you're welcome to use it. One option, the one I'm not going to keep using, is to get a single fraction on top and a single fraction on bottom. Okay? So you're going to combine the denominator all into one fraction. You're going to combine the numerator all into one fraction. So if you do that, the denominator in the numerator would be a 5. So we would change this to being 5 over 5 minus 7 over 5. And the fraction in the denominator, this would be 7 over 4. This is a 2 over 1. I'd multiply this one by 4. So I'd have 8 over 4. It's addition plus 8 over 4. Okay, so I'm turning all of my little pieces into their own fractions that I can combine. So in the numerator, this is what you were thinking about, Cameron. We're going to keep that denominator 5 the same and subtract across the top. 5 minus 7 is negative 2. And in my denominator, I would be adding across the top 7 plus 8, which would be 15 over 4. So if you like it this way, this turns it back into the exact same thing we were doing over here. And that is friendly. There's nothing wrong with that. You can totally do that every time. So if you want to do it that way, what we would do next, of course, is we'd take our negative 2 over 5, and we would multiply by the reciprocal of 15/4, which is 4/15. Looking across diagonals, nothing is good this one, right? Everything just doesn't simplify. So we'll multiply across the top, we'll multiply across the bottom. I think it's 75. We get negative 8 over 75. Okay, everybody understand what I did? So there's nothing wrong with that method. It's just not the one that I use because I like the other one better. I think it's a little bit cleaner, a little bit more straightforward. So I'm going to shift this up. It's not disappearing, but I'm going to rework the problem in a slightly different way. Now, I've actually shown you this before, but it's probably been a month since we encountered problems that had the need to do something kind of like this. And what I actually had us do is we found the least common denominator of the denominators, so the 4 and the 5. They have nothing in common, right? If we were adding fractions together and we need a common denominator, we just have to multiply them by one another. It's 20. Okay, so far so good? LCD is 20. And what I'm going to do is I'm going to multiply the numerator by 20 and the denominator by 20. But as I do that, I have to multiply each term in the numerator and each term in the denominator, like that. So it might be more helpful instead to simply write the 20 next to each fractional value and whole number value. So if I do it this way, 20 times 1 is 20. When I multiply the negative 7/5 times the 20 here, when I multiply these, they reduce. The 5 cancels with the 20, leaving me with a 4. Does that make sense? And then if I multiply my negative 7 times my 4, I get negative 28. In the denominator, when I multiply the 20 and the 4, right, the 4's in the denominator, so they will reduce. That 4 goes evenly into 25 times, so I'm left with a 5. 5 times my 7 is 35. And then I have 2 times 20, which is 80. The reason I like this method is because it eliminates the fractions quicker. Now, I don't have fractions inside of fractions for quite as long. That's why I like it. We'll do our subtraction. We've got negative 8 on top. And on bottom, I have...
Isn't it 40?
I was like, it shouldn't be. Sorry. Where did I even get an 80? No clue why I did that. Yeah, that's not even a zooming in and zooming out error. I can't blame it on that at all. I have no idea what I was doing. 35 plus 40. Yeah, 35 plus 40. Heavens to Betsy. How about 75 for my denominator? So if you don't like that method, it's okay. You can do what I did earlier. That will be just fine. But this would be a second option. So I'm going to keep using that option for at least a couple of them. Then if anybody's really dying to see me do another one a different way, then we'll just do a different way. But looking at the denominators, there's actually 4 superfractions here. I have a 5, a 2, a 2, and a 4. So I need the LCD of 5, 2, and 4. What is the least common divisor, least common denominator of 5, 2, and 4? It's actually 20 again. Right? It's the first multiple they have in common. A least common divisor is the same thing as a least common denominator is the same thing as a least common multiple of numbers. It's 20 again. So I'm going to multiply by 20 on all of the pieces. And in all the cases that I've multiplied by 20, they're going to simplify. So this 20 and this 5, 20 divided by 5 is 4. So this one's going to cancel to give me 4. This 20 and this 2, 20 divided by 2 gives me 10. Over here I have another 20 divided by 2, so I have another 10. And over here I have a 20 divided by 4, which gives me 5. So now I'm going to multiply. Let's see if I can keep track of all my numbers. 4 times 6 would be 24. It's subtraction. 5 times 10 is 50. In the denominator, 10 times 3 is 30. Subtraction again, and 5 times 5 is 25. Okay, I think I caught them all that time. So we're going to subtract. What is 24 minus 50? Negative 26. Good. How about 30 minus 25? 5. And then do 26 and 5 reduce? No. Improper fractions are perfectly fine, so we can leave it as negative 26 over 5. Okay. Now, when I move into number 5, you'll notice that on number 5, again, I have a single fraction on top and a single fraction on bottom, right? Yeah? So as I'm looking at this problem, it's far more like problems 1 and 2 than it is on 3 and 4. Yes? Single fraction on top, single fraction on bottom. So I can take and leave, or I can leave, rather, the numerator the same, x plus 4 over x minus 5. And then the denominator, I would change to multiplication, and I would flip it. So it's 5x to the 4th over x plus 4. Okay, is that step, just the rewriting step, okay? So looking across diagonals, do we see anything that we can reduce on this one? Yeah. Yeah, they have a factor, not term, but a factor in common. There's an x plus 4 in the first numerator and an x plus 4 in the second denominator, and they cancel because they're identically the same factors. The other diagonal doesn't have anything, right? When things cancel, they're left with 1s. They didn't really cancel and disappear to 0. So I multiply across the top, and I multiply across the bottom. Any questions on that one? Okay, again, this one looks a lot like the other ones, doesn't it? The earlier ones and that very last one I just did. Single fraction on top, single fraction on bottom. So when that's the strategy, we're going to leave the top the same. We're going to turn it from division into multiplication. And what will I be multiplying by? Thank you. The reciprocal, which is 2 over 2x minus 10. Okay, so if I look across diagonals, nothing simplifies, correct? But do you notice that that second denominator has a 2 in common to both of its subtractional pieces? Yeah? So some of the things that we did before are going to show back up again. I am able to factor this denominator by taking a 2 out. And when I do that, I can either cancel the 2 now here with the numerator, which is what I'm going to do, or you could cancel it along the diagonal if that's what worked. Okay? Here they both work. I'm just going to cancel top and bottom. That's the only thing that simplifies. So across the top I have an 8. Across the bottom I have a 5x, and I have an x minus 5. You could multiply them out if you wish, but you do not have to. If you leave it in this form, it's far more obvious that it's reduced than if it's multiplied out. You can see there's no way it simplifies. Does that make sense? Okay. Number 7, same thing. I've got a fraction on top and a fraction on bottom. So on number 7, I'm going to rewrite the top as 7x minus 49 over x. And then what will I be multiplying by? X minus 2 over 4x minus 28. So this one feels like the last one. I have pieces that are not sort of in their factored form. That very top piece right here, 7x minus 49. What can I factor out of 7x and 49? 7. So I'm going to pull a 7 out, and I'm left with x minus 7. Is there anything else I can do like that? The 4x minus 28. What will factor out? The 4, and then x minus 7, exactly. So we can compare top to bottom. We can compare across the diagonals. What do you notice that will simplify? The x minus 7 simplify. Anything else? Not on this one, right? None of the other diagonals have common pieces, and from top to bottom, neither do they on that. So I have a 7 on top and an x minus 2. And I have a 4 and an x on bottom. And if you don't happen to notice anything else canceling out, but then you get over here and you notice that something does, you can still cancel it in this form too. But if you get over here and you recognize, oh, look, I didn't realize it. It's still even on top factor and there's an even factor on bottom. Well, then you just cancel it there and you do another step. Okay, you don't have to go backwards. Okay, so number 8. Number 8 is not the same. Why not? Yeah, it's got variables. Okay, so some of ours lately have had variables, but it's also got the addition that problems 3 and 4 had, right? So over here, if you wish, like we did on 3 and 4, you can do it where you get a single fraction on top and a single fraction on bottom. You can do that. That's okay. But what you could also do is you could also look for a least common denominator. So we're going to practice that on this one. Notice this is 3 over 1. This is 7 over 1. I need the least common denominator of the denominators of which there are only 1 and w. That would be a divisor. I need multiples. It would be w. Yeah. So the least common, this is terrible because denominator and divisor have the same d. But the d here is talking about the denominator. They have to have denominators that are in common. So I have a denominator that's in common. It's going to be w. So what I'm going to do is I'm going to multiply, like I did with the 20s, w by each of my values. And it actually works out really nice. Because what you'll notice is that this w is multiplied and this w is divided. So what does that mean happens? They cancel. And it happens here and it also happens here, right? Divided and multiplied. On these over here, it's not actually divided, so it doesn't go away, but that's okay. Those actually happen to have a denominator of 1 anyway, so that's fine. So on the top, this is the number 1, so 2 times 1 would be 2. And then I have 7 times w, which is 7w. And then I have w times 3, 3w. And then I have, this is not written that way, but This is an understrip 1 right here. 2 times 1, which is another 2. And I know there's probably a handful of you who'd really like to cancel the 2's or cancel the w's. That's not okay. And I know I've said it before, but I'm going to say it again because some of you are going to still try and do it at some point. You cannot cancel terms. You can only cancel factors. And remember, it works like this. If I have 2 plus 3 over 2 plus 4, and I attempt to do that kind of a cancellation, I would get 3/4. But if I actually add them together, I get 5/6, and these are clearly not the same. No term cancellation allowed.